Okay, welcome back. We're still talking about our named gas laws here, and this is our third one for it, and it's going to be Gay-Lussac's law. Sometimes they even call it the unnamed gas law because there were so many people working with gases and their relationships that sometimes they don't give the credit due to our next one for it. Now, before we start looking at the gas law, let's look at the relationship first. So we have four different flasks here for our Erlenmeyer flask. Each one is filled with the same volume for it, and they're at the same pressure. Now, each flask is allowed to heat up to the temperature shown on it. Which one would most likely have the greatest pressure? So if we think about our gas particles, and I draw 5 right here, if I start increasing the heat for it, what's going to happen to them? Well, they're going to start to move faster and faster and faster. The faster they move, the more collisions they're not only going to have with other gas particles, but they're going to have with the sides of the container for it. So which one would most likely have the greatest pressure? We would see it would probably be number 4 because it would have the highest temperature. So what does that mean for our next gas law? Well, Joseph Louis Gay-Lussac was a French scientist working around the 1800s. He said pressure and volume are directly proportional. That means as one goes up, so does the other. As one goes down, so does the other for it. So, as pressure increases, so does temperature. And remember, we can use our PTV stick for it. So, with Gay-Lussac's law, we're keeping volume consistent. So, as our pressure increases, notice that our seesaw of T also goes up for it. If pressure decreases, our temperature is going down for it. So, I'll write it out. As pressure increases, temperature increases. As temperature decreases, pressure decreases for it. And we'll see that since it's directly proportional, it makes sense that the formula looks more like Charles' law than Boyle's law for it. So what Gay-Lussac said, pressure and temperature are directly proportional. So if we're using our PTV stick like so, put your finger at volume because it's kept constant. And then if you pull up the P side, what happens to T in the middle? It increases for it. So remember that our PTV is really great to look at our different relationships for it. Now, our combined gas law is the last one that we're going to look at. So what does it mean if you combine something? So whether we're combining something in the kitchen or combining paints in our studio, we're going to see it's a mishmash of all different stuff coming together for it. So our last other important gas law is the combined gas law. It's not only going to use pressure, volume, and temperature. So we can't use the PTV with our combined gas law because it combines pressure, volume, and temperature for it. AKA, we're going to combine our Boyles, which is our P and V, our Charles, which is our V over T, and then Gay-Lussac, which we just looked at, is our P over T, into our combined gas law. So we can notice that the formula looks very similar. We have our P1V1 on top like Boyle's, we have our P1T1 like Gay-Lussac, and then our V1T1 like Charles. Remember, the ones represent our initial conditions, whereas the 2 represents our final conditions. So we're pretty much just putting Charles, Boyle's, and Gay-Lussac's together for our combined gas law for it. So now that takes us through our final 2 gas laws that we're looking at conceptually, Gay-Lussac's law and combined gas law. Thanks for watching.